Joint WebGL and GLTF Birds of a Feather session here at SIGGRAPH 2016. It's a pleasure to have you all. So I'd like to introduce all of the working group members that we have present today. We have Corentin Wallet from the Angle team at Google, Neil Trevitt, president of the Khronos Group and member of NVIDIA, Jeff Gilbert from Mozilla, Zhenyao Mo from Google, Jamie Medill, also from the Angle team, Changkun Miao from Intel, and Jeff Lang, also from the Angle team. Can you see everybody? All right, so we would like to preface this Birds of a Feather session with the big news, all right? And this couldn't have been done without the dedicated work of dozens of individuals from many companies, all right? But the WebGL2 conformance suite is passing 100%, and this is a long time coming, so that's it. And again, all of these individuals contributed just tremendously, and many more. We can tell you a little bit more about the details, but really look these slides up on the web afterward because we're running really short on time today. Tons of new features that come along with OpenGL ES3, but these are really well tested at this point in multiple browser implementations, Firefox and Chrome, due to, again, incredible dedication by this team. And I'd like to acknowledge everyone's specific contributions here, including Shannon's, project manager of the Angle team. But a few concrete thanks. Zhenyao Mo, who worked for over a year on Chrome's OpenGL ES3 implementation and really got it to 100% conformance and has been tireless in his investigation of the WebGL2 conformance suite issues. And I'd like to also really acknowledge Changkun, who, along with the team at Intel, has made tremendous contributions to the conformance suite itself, and without whose contributions we would not be here today. So all of these features you will be able to rely on working 100% identically across browsers and operating systems, again, because of all of this hard work. The release is almost here. I anticipate only a few more weeks before both Firefox and Chrome will be able to enable WebGL2 by default. And so the call to action to you developers is, please get your content ready. Try out the nightly builds, turn on the functionality, upgrade your applications to use 3D textures and transform feedback and integer texture formats and all that cool stuff, and let's drive forward into the future. So again, many thanks to all of these fantastic individuals. We wouldn't be here today without them. And now okay, maybe we have just a couple of quick minutes. Let me just play this video for you. Oops. So this is a demonstration of a transform feedback simulation that's running in WebGL2 and WebVR, thanks to our colleague Brandon Jones, who unfortunately couldn't be here today. All right, but all right, we're talking 1 million GPU simulated particles running inside WebVR. And if I may point out, this also works great on mobile devices, like this Pixel C, which you can purchase for a very low price on the Google Play Store. Please welcome Yuri from the Blend for Web team. These folks have been successfully bringing Blender content to the web via WebGL for years now. Oops. Thank you.
Thank you so much. My name is Yuri Kavilev. I'm the founder of Blend for Web. And today I'd like to say a few words about Blend for Web, what is it, and what was our updates last year. So a little bit of background here. Blend for Web, we in Blend for Web work with WebGL quite a long time, and the first release was 2 years ago. So Blend for Web is a WebGL engine basically written in pure JavaScript. And it is a self-hosted solution and open source too. And the main distinguishing feature of Blend for Web is that it is organized around Blender. So we basically use two main formats, and one is HTML, just HTML. HTML files pack everything you need to open in a web browser, so it's perfectly suited for sharing offline. And a format which we called simply JSON, and this format is optimized for loading via internet. So, and the pipeline basically looks like you author content in Blender, you export and you open it just like this Pokemon. It has animation, export, Blend for Web HTML, and open this HTML file in your preferred browser. So here you see also some interface, and that's it. So our goal is make WebGL as artist-friendly as possible. So one tool you already seen, this is WebPlayer, lightweight application for sharing, for embedding into web pages. And other tools for artists are also essential. And one of them is a material GLSL editor, which allows you basically to create materials so without any programming. And Logic Editor, which allows you to create interactivity without any coding. So that's why typically Blend for Web is chosen by artist-led teams. So here is a small example of web player and the Logic Editor created by one of our customers. Here is a very simple animation. This is just clicking, changing colors, but still it was created without any programming. So, and another example, now this is a GLSL editor work. The most prominent material here is a diamond, which was very difficult to create, but still was created by artists without actual writing GLSL code. So, and another demo I'd like to show you is we created recently, is called Dairy Plan Demo. And it's rather big graphical application, a lot of animation, still works on smartphones. And this reproduces an enterprise technological processes, how milk actually done, its equipment, how it works, how it is connected, and animated and so on. So it's a rather big application. Games also possible, so we got physics. We got web audio, we got a lot of other features useful for games. And here is a game example. So it's called Pettiger's Tale and was created as a browser game. And here you see animation, character, and jumping, cool particle effects, so on. We work with WebVR as well. So Blend for Web supports both old and new specifications, and we got a VR mode button in the web player for artists, and we also have a graphical configurator for configuring gamepads, which are essential for web VR experiences. And here is a very small demo. It's a game called Space Disaster, so you are flying in space and shooting asteroids, and this can be done in web VR. And you can see also here a web camera output on a texture in a 3D space. So I'd like to finally, thank all the creators of WebGL, because we enjoy WebGL very much, as well as our users. And I'd like to mention that NASA's Experience Curiosity, a Blend for Web powered application, recently won a Webby Award, and so it's safe to say that WebGL is now an award-winning technology, and thank you very much.
All right. Next, I'd like to welcome Johannes Schmidt from Esri, and he's going to talk to us about globes and geo stuff in WebGL on the web. Here's your time. Thanks.
Cool, thanks. Yeah, as Ken said, I'm going to talk about how we use WebGL at Esri. Just a quick introduction, Esri is a major player in professional GIS and has been for more than 40 years now. And we've traditionally been very strong in desktop 2D GIS, but in the past years, we've made a real strong push for bringing 3D GIS across the platform so that users can create their scenes with powerful desktop applications, but then publish them to services and consume them from browsers and mobile devices through one of our APIs. So talking about WebGL, I'd like to start with one of our desktop applications, which is City Engine. It's a tool for procedural city modeling or city modeling in general. And it's a very heavy desktop application, and we got the user requests that they wanted the lightweight viewing applications to present their work to their customers. So that was around the time that WebGL was released, and we thought, hey, why not give it a try? And that try actually ended up with a product called the City Engine Web Viewer, which we released in end of 2012. That just allowed the users to publish their scenes from outside of City Engine into a cloud and then consume them directly in the browser. But this was one monolithic download, one monolithic scene that you could just interact with and look at. Now, at the same time, Esri has a successful 2D mapping API for JavaScript. And because our WebGL experiment, the City Engine City Engine Web Viewer was such a success, we decided, why don't we extend that mapping API to support both 2D and 3D at the same time. So that's what we did, and we released this in the first version in the JavaScript API for ArcGIS 4.0 earlier this year. And enough of the slides. Now I'd like to show you some demos from that. All right, so this is an application that we call a story map, which is really for our customers to kind of tell a story to their users. But I'm just using it to show you some of the technical details. So please ignore that. But yeah, we have like a streaming globe render. It streams terrain and tiled maps. You know how that looks. We allow users to overlay. Should have preloaded that a bit more, I guess. We allow users to overlay map data onto the globe, both like raster map data, but also 2D vector features. But then, of course, the fun stuff comes when we add actual 3D features into play. So this is a scene of San Diego. You can see the convention center here that's being streamed in from a web service that we developed at Esri in real time. You can see there's nice trees and nice looking textures. We also allow features of any kind, 2D and 3D, to be styled based on GIS attributes. So typically our users have data attached to their features, and in this case, for example, this could be a visualization of the growth projections with colors. Oops, I wanted to go here. This is another example of that. Here the input data set is just 2D polygons of counties in a certain region, and then we have some additional data, like here, for example, the percentage of population that is in poverty in these counties. That both drives the size and the color of these extrusions, but you could also do multivariate visualizations where you use a different attribute to drive the color and the size. Here's another typical scenario that we face. So this is Philadelphia, and you can see it's a kind of a backdrop of buildings there. Construction site where they tear down old buildings. They want to propose a new development, and they may have like different variants of these developments, and they want to engage with the citizen of the city. So they want to put it on the web, and then you can like easily with these slides you can sort of take them through a story. You can also look at the shadow that a building will cast at a given time of day, so that maybe people can complain that their backyard is in shadow all of the time after the construction. Here's some more like technical gimmicks. We've done some fun stuff like realistic atmosphere simulation and nighttime stars. I don't know if it's very visible. That kind of stuff, the fun stuff to do. We have kind of two different operating modes. One is what we call the global view, which is what you've just seen in the past examples. The other one we call local view, which is essentially a Cartesian view on a scene, and it allows us to show data in any given projected coordinate system without us knowing how to actually reproject it. It also allows the user to clip the scene to a certain extent, And what's really cool is it allows the user to go underground. So this data here is a map of oil and gas wells marked with the little crosses, and then the earthquakes in the vicinity marked with the circles. And of course, it's really nice if you can actually analyze at which depth the earthquakes have happened and how far down the oil wells go. All right, finally, this is another nice little example. Oh yeah, that shows really well. So these are all the satellites around the Earth. You can filter them by what's chunk, what's not chunk. You can filter them by orbit. I don't know, you can check out which country has the most satellites in space and which country has the most chunk in space, I guess, as well. It doesn't do the numbers here, so that's all good. Yeah, and that's it for me. Oh, sorry, I forgot. I have one more slide. There's the links to the resources if you're interested, and the links to all of these demos, but they will be available on the website.
Yes, I thank you, Joe. Fantastic stuff.
Hi guys, so I'm Alban, co-founder and CEO of Sketchfab. Very excited to be here today. For those who are not familiar, Sketchfab is a platform to publish 3D files on the internet using WebGL. I'm just going to start by sharing a quick milestone we just passed, that we reached 500,000 users on the platform, which probably makes us the largest community of 3D creators on the internet, and we're very close to 1 million 3D files, which also makes us like the largest library of user-generated 3D and VR content on the web. So we've really focused the past year on VR. And a year ago at the WebGL Buff, we announced our VR button in our player. And today, we just released like half an hour ago, our VR browser, which is kind of our master plan part 2, moving from just a VR button in a single player to a VR interface on the entire site, which means you can browse Sketchfab in VR. So I'm just going to show you very quickly. So here I'm in the main browser of Sketchfab, and here is like the View in VR button, and it's going to open a VR interface for the entire site. It works with any headset, and yeah, we can just spend hours browsing the site in VR. Oh, I don't know what I entered. And the View in VR button is going to show up on any gallery, collection, username, yeah, letting you stay on a user in a VR context. Instead of having to remove the headset between each model. So a quick example here, for example, with the British Museum. Loading the page. And they are publishing hundreds of artifacts and collections in their Sketchfab account. And now I can just go to their VR channel and just swipe through their models in VR. And it means that anyone who publishes stuff on Sketchfab can view his own creations in VR on any headset from the web. So the next thing we also just released is teleportation in VR. Originally, you could only like walk around or look around. And now we added teleportation, what's really cool is that we have visual feedback for the controllers. So if you're on Vive, you're going to see the controllers. And basically, you can teleport yourself anywhere in the scene where you look by just clicking on the trigger, or on cardboard or gear, just tapping on the button, which makes the navigation much better as well. We also released the VR scene editor, which means you can very easily set up your scene in VR, mostly like defining the scale of the scene and like the initial viewpoint of the scene. I'm going to try to load the editor just to show you very quickly. Sorry, it's a bit long. I'll let it load. So yeah, and so that's the three main things we released for VR. So the VR launcher, teleportation, and VR scene editor. And of course, we've been working on many other things. Just added depth of field, which means you can add some blur around the model, and it's a very cool post-processed effect in the player. I can show you briefly here. Still loading there. And the depth of field is super awesome, like on large scenes where you want to give the kind of same effect as what you would do on a DSLR camera. We've added support for morph animations. I'm going to show you that as well. I'm going to load the several things. Here is an example on the depth of field. I'm not going to load them all. Here we go. So that's my VR scene editor, and so you can see, so that's a scan I made in Paris, and I can very easily edit the scale, move the little man wherever I want on the scene, and yeah, adjust the place where he is, and it's going to define how my VR scene loads when I start it. Up. And then, so that's an example of the morph animation that is loading. I have 1 minute left. Right. And then, yeah. That's just more examples of the blur. I'm loading my Matt Fat Bat. Come on. Almost there. Sorry. I have 50 seconds left, so I'm fine. Okay. And so yeah, I feel we're missing the sound on this one, but that's something we plan on working on as well. And you can see a bit the depth of field, I guess. I'm still loading the textures, but it was just to show you the morph animations. And then yeah, we just released the support of combining annotations with animations, which is something we didn't add before. And by the way, we also now support our annotations in VR, which means you can save preset viewpoints in VR and add some text info on top of that. Yeah, that's it. Thanks.
Tarek Sharif works at BioDigital in New York City, and they're doing, I don't know, all sorts of biological visualizations.
Anatomical visualizations.
All right, fantastic. Take it away.
Okay, cool. Yeah, so as Ken said, I work at BioDigital in New York. Quick intro to what we do is basically creating these kind of like interactive anatomical visualizations. You know, let people, like part of it is like, you know, just let you drill into the data, kind of get ideas about how it's put together. It's like an educational tool. And a lot of our stuff is about kind of allowing users to create custom views and annotate things and create kind of the scenes that they want to see. So the basic goal is to kind of make this sort of anatomy data more engaging for users and to make it accessible to people through the web. Our platform, basically we have a team of 3D artists that create these models. Our rendering engine is built on Scene.js. And then we have the users come in and create kind of the custom views and annotate things and share them with each other. Our key clients will be medical device manufacturers and pharma companies who will get us to basically you know, create kind of custom interactive scenes to train doctors or educate patients about how their stuff works. And then of course there's the like med students that love our stuff for studying. And then a big part of what we do is what we're trying to do is kind of allow people to use our tools to kind of create their own experiences. So we have kind of a JavaScript API that like, so this scene, it's like loading our rendering engine in an iframe, and then we have a JavaScript API that lets lets people kind of really integrate into their page, like update the scene through external events. So one of the key problems that we had, getting to what I want to present, is like, so our data tends to be quite big. With clients in medicine, like we want the textures to be detailed. We want it tends to be pretty big geometry. And with that morph data that you saw, the beating heart, like there's a lot of stuff that has to be downloaded. And then it tended to be pretty rigid. Like the way we were working before, it's basically like our artists create stuff in Maya, and the user would have to wait for that scene as it was created by the artist to kind of be downloaded before they could start interacting with anything. So our solution was to kind of fix our back end to allow us to basically stream assets in piecemeal. So the artists still get to create the scenes the way they see fit. There's a little bit of normalization to make sure that stuff kind of fits together in the same world, but they basically get to use the tools like the way they did before. And then on the back end, we make those assets that they create, the geometry, the animations, the materials, individually addressable. So I can just request whatever asset I want. So the architecture, it's pretty simple. It's basically the artist creates something in Maya. We have a little bit of pre-processing that happens to make those assets that come out of Maya addressable via like a URL. And then we have a WebSocket now between the client and the server to avoid too much HTTP overhead for all those requests. And then this has allowed us to kind of open up the sort of applications we can create. So one of the kind of very simple advantages we get is that you can gradually, I'm running out of time. You can gradually build up the scene, which I'll show you a demo of that. The client can only load what it needs, and then our artist can create these separate scenes, and we can kind of create mashups between them to give our clients what they want. So here, the moment of truth. See if it actually downloads. Okay, it's coming in a bit slowly. All right, a little bit anticlimactic. But basically, like the idea being that like we used to have to kind of download all this stuff at once before the client was seeing anything, and now we can do it one by one. Hopefully these demos will work a little better. So this one, it's kind of a demo of like, so we have these different versions of the heart that live on our server. And if I want to kind of switch one version for the other, is this actually gonna? All right, so it's coming. But basically the idea being that like these things can really be created independently, and we get this like basically kind of one big scene that can be dynamically built up out of all of our assets. I'll try to show one more. See how this works. So this was one we were kind of excited, like this is sort of a use case we want to play with, which is the idea of like having a patient timeline. So the idea being here that like, doctors showing, one of his patients how their condition has changed over time. He lost an eye, I guess. Had a bad day. So, okay, yeah, stuff comes in, and then you have like, yeah, you can keep kind of swapping objects in and assets in for other assets. So I recommend going to the website on a better connection and checking out how it works. Yeah, so that's basically, oh yeah, maybe I'll just show you the YouTube video, my last 20 seconds of what it's sort of supposed to look like. Is that one gonna work? Yeah, so that's kind of what it's supposed to look like if things are streaming in a bit more quickly. But yeah, so that's essentially it. Oh yeah, if you're interested in checking it out, this is our dev website. Try the API. And that's it. Thank you very much.
Let's see. Right. Hello, everyone. It's just as a this is just a little update of what has happened over the last year on the library. So it's 3 years. It's an open source JavaScript 3D library, and it's the 6th year that we've been like running it. And on the last 6 years, some of the things, like we have done like a ton of like loaders and like many like improvements to it, but like I just wanted to highlight a couple of major visual improvements. So early, kind of at the end of last year, we got to finally improve how the shadow map looks like. So that's how it used to look before, which was like basically the shadow map. All of them will like get on, like black on top of each other. Will be a little bit of like masking on top of each other, and then after like refactoring a little bit the whole thing, it ended up looking like it's supposed to be, which like there's no light where there's a shadow. Another thing was like we got to add shadow maps or like point lights. Also get like we added like shadow map support to point lights, so it just renders to a cube map. Another thing was physically based materials. Finally, like it was a work especially with Benny Houston and Wes Langley. So with one texture, for those that you don't know how this works, like basically with a couple of textures, you define in your model like whether something, how much is reflective and how much smooth it is or not smooth it is, and like. It doesn't matter, like you can put it on any environment and it's always going to look like how it's supposed to look like. And like the last thing is something that we're working right now, which actually we just did pretty recently, thanks to Rich Harris, which was like refactoring the whole, well, basically making the whole library modular. So you're using like ES 2015 modules on your project, then whenever you compile, it's only going to use whatever you need. Like you have the option of not having a single build like library. Usually you have like a single build, but like now you can just pick whatever you actually need at compile time. Wanted to feature a couple of projects. Audio isn't working. Anyway, let's see if we can fix that. So okay, I think. Did that work? Try again. No, anyway. So Google did a project with Star Wars for promoting the latest movie, and in this case, it goes behind. Anyway, so in this case, you will use your mobile phone as a lightsaber, and it will connect it through like WebSockets, I think it was. Through your application, so you basically like kill all those, like fight all those soldiers, right? Using your lightsaber. When I saw that, I actually was impressed because I thought it was a video, but then it turned out to be real time, so that's quite a good thing to be impressed by. Here's another kind of funny one. Let's see how this works. And if the internet works with us. So this is a real-time music video that uses, well, now you'll see, gets a picture of yourself. It's going to be creepy. You should check it out. Here's another interesting one where it's actually also a promotion for a movie. What I found interesting about this one is that we are used to, websites that you scroll up and down, but on this one, when you scroll, you scroll backwards or forwards. So by scrolling, you can like going into different parts. You know, I can scroll back in or back out, and you can see the whole website as a C kind of like projection. So this is some of the sections. I'm scrolling pretty quickly through all of them. Yeah, you get the, yeah. It's pretty nicely done. 40 seconds. Another promotion for a movie, which, yeah, maybe skip that one. You should watch the movie, it's pretty good. And only 30 seconds, so I'm gonna like skip to the end. So if you ever like, we have support. We had support for WebVR for quite a while. We've been supporting like Oculus and HTC Vive devices. And one problem that I had with that was that you're also usually carrying your device in order to test. So this is the web, so we can like do whatever we want. Like we can do any kind of like emulation of like any API. So just 5. So we come up with we did this extension with my friend Jaume Sanchez where you can, because it's an embedded from an embedded, okay. Let's try here. So we basically can emulate, we're emulating the WebVR API, so you can move the camera from here, the rotation, and whatever without having to connect your device all the time, which we just found like pretty handy. And almost done. Oh, where did it go? And something I've been also like working on is adding WebVR to the editor. So you can have like on the editor you can have some projects, and you can like publish them from there. So in this case, like you can add like. It has like a WebVR support, so whenever you publish this, you're going to have the option to entering VR down here. But also on top of that, I've been working like a VR mode of the editor itself. So still like have to add interaction, but like here you have like a, let's see if I can click it. Yeah, here you have like what will be the whole UI is like part of the scene, and you can just click on the things and like modify things like right inside VR. Yeah, that's about it. Cool, thank you.
Yeah, I'm Sean Lilly. I'm a 3D software developer, and I work on Cesium. All right, so Cesium, if not everyone is familiar, it's an open source JavaScript library for world-class 3D globes and maps. And it's built on WebGL, which is why we're here. And we have a bunch of different demos that we've seen built with Cesium. So I'm not going to go through all these, but we have like satellite view, similar to what you saw earlier. I guess one cool thing is like the NORAD track Santa on the bottom, where WebGL reaches 20 million people on Christmas Eve. So it's a good test case for like who can run WebGL, and it turns out a lot of people actually can. And yeah, so we use GLTF. You're going to hear a lot more about this in the other presentations, but basically for the models that we load in Cesium, we're using GLTF. And there's a lot of tools, and there's a lot of a huge ecosystem for GLTF, and it's growing. Recently, we've been working on some tools such as adding ambient occlusion to models, baking ambient occlusion into the vertex attributes. And you can check out that repo. But we also have tools for compressing like the position attributes just to make GLTF models even smaller. So sort of the whole point of Cesium is to both render every building in Manhattan to every satellite in space, and then everything in between. So we can render like 1 million buildings in New York City, point clouds, high-res train and imagery, instance tree models using the angle instance arrays extension, and 3D vector data. So this sort of goes into 3D tiles, which is our format for streaming this heterogeneous, massive data sets. So I'm going to quickly go through a showcase of what different people have been doing with 3D tiles. If you saw this before, this is like a condensed version. Okay, so first up is Bentley. They're using context capture to basically take aerial imagery and then create a 3D mesh. And it's using 3D tiles to basically stream the models and imagery. And you can see it's pretty high detailed. Like if you zoom into the truck, you can almost see the things that are in the back of the truck. All right, next, this is Swiss Topo. This is part of the Switzerland government, and they're using 3D tiles to render 1 million buildings that are just on the countryside. Yeah, pretty short one. So next up, this is sort of a demo we show a lot, which is rendering New York City using CityGML buildings. Here you can see, like, as you zoom out, the different LODs, or it's rendered based on the LOD, and then you can select and hover over individual features in the city, and you can then load up the actual attributes for those features. So this building, you can see like what the properties are for that building, and it's easy to style these buildings. It's simple as like a texture change. You can also hide certain things based on certain criteria. So here we're just doing it based off the height of the building. And yeah, just simply styling based on different palettes. All right, so this, yeah. The next demo is Vricon. So this is sort of similar, but instead of having like 3D buildings that are all separate, this is kind of like a fused approach of terrain imagery and buildings. So they use digital globe data, and they basically reconstruct the 3D data from images. So that was quick. But OK, so this is virtual city systems. This is showing both a point cloud and a 3D buildings data set working together. So this is kind of like what 3D tiles is about, like using point clouds, buildings, and a bunch of different other tile formats all together. Yeah, so here you're just zooming in, seeing the textures. And this is one of our first users, CyberCity 3D. So they do smart city planning. And here it's just selecting basically what buildings are being built, what are in progress, what are being planned, hiding and showing and changing colors, and also using the Cesium API underneath to basically style and show the districts, or at least the development plans. OK, so that was just, yeah, a quick video. Thanks for everyone who used 3D tiles and made a demo for that. So if you want to learn more, we do have the specification on GitHub. I didn't go too much into the technical details, but essentially it's a spatial bounding volume hierarchy. It's using WebGL, of course. You can render massive models like this duck. And also, feel free to join us at the Khronos after party. It's from 6 to 9 today. It's I guess right here. And we'll have a VR demo. So you've seen some other things, but we have a few Google Cardboards to check out. And that's it. Thanks.
Thanks, Sean. This is great stuff. It's really exciting to see how many domains WebGL is reaching, and that Cesium is reaching, and also Esri. So soon we'll see not just the exteriors of buildings, but interiors. But because somebody has to catch a flight, I'd like to introduce Remy Arnaud. Where is he? Remy works at Starbreeze, and they've been working a lot on GLTF. Remy is one of the people that spearheaded the GLTF specification, and he's been thinking a lot about streaming GLTF models to the client recently, and has some pretty cool demos, which I'm sure are going to work great, and they'll even work great over a limited internet connection.
Thank you, Ken.
You ready?
Thank you so much for squeezing the presentation. I have Nintyan Selim is watching us right now, and I told him that if he was able to finish just before SIGGRAPH, I would try to squeeze in the presentation, so thank you, Ken, so much. So there's a presentation, but I'm not going to show the presentation. I'm just going to go to the demo. So lucky for me, there was a presentation just before about 3D streaming of data, and so that's the same idea that you had a presentation about. Using standards in that case. So on the left side, you have your content on the server, which would be Collada, and there's the GLTF format that we've been talking about, that is the transmission format to the client. But what we do here is we add the extra step of streaming the content. And in that case, what we do is we reverse the kind of client server. What's happening is the server understands the format, the GLTF format, and the client is going to ask the server to which part is interested, and then the server is going to feed the client with different pieces, and the client will have to react to those parts and build the model as is received the model. So as a standard 3D, I don't know what that is, 3D GLTF, FreeJS viewer, and we have a little JavaScript library that will open source and that you include. So instead of saying load this model from this HTTP, you say please spoon feed me with through WebSocket the model that is located at this location. So that's slider here is, but I did not need it. It's the slow my internet please slider. And so if I actually start the process, I've been asking for this model to come, and it will load different parts. So it's pretty, I mean, if you don't slow the internet, it goes very fast to load. But I'm going to do it again, very slow internet. What you're going to see is the model is going to come up with different parts of the geometry, and then there will be the UV mapping, the normal mapping, and then the texture will come in, and then the animation will come in bone by bone, actually, in that case. All right, so let's do that again. And restart, revert. Where's the reset? Okay, reset, start. So with a slow internet, simulated, and it's really slow here, and for the simulation. And you know, it's just an example. So why would we want things that in that order? What we want to send the animation for one bone and then from the other bone, and why would we not want the animation first? Maybe if so the whole project is to look at what are different ideas of streaming can be input to make it very useful for end user. Because I mean, as you've seen, you know, streaming is of course understood. It's like I don't want to be waiting to have my whole model there before I can use it. So, but if I'm an animator, maybe I will want to first see I don't care about the textures and the I don't really care about the textures and the polygons. I maybe want to have my animation first. So let's do that. Let's try this model. And I'm going to start it. Where's the start? I can't get my buttons. There you go. And then what I do is I just want to see the skeleton of the model. And so now what's happening is I'm getting my animation. I can already start using my model. And because the idea is to have a web browser for 3D content, I can skip very fast to the next, you know. And within the first seconds of what I'm looking for, of loading the model, I can already see the animation, because that's what I'm interested into. Now, imagine you're looking at a building and you want to know placement of things within a building. So if you load that model, which is pretty standard, when you start loading the model, it comes in those different parts. Now, how do I want this thing to be sent to me instead of like that? Well, maybe I'm going to order it by bounding box. When I do a query to the server, I'm going to say, you know, actually don't send it to me in that order, send it to me with the largest model first. And then in that case, you're going to get the whole size of the building, and then now you can see the things building up inside, right? So that way I know exactly what the building is and what it looks like, and I can skip to the next one if I don't have to wait, right? So that's the idea of streaming, and you can apply it in. And then we're looking at different way for the client to tell the server how it wants the data to be sent to it. So that's promise I'll be short. That's it. It'll be open source pretty soon. Thank you, Ken. Thanks a lot.
This is great stuff. I mean, you can see a common theme here. People want the content streamed to them. They don't want to have to wait for the entire thing to come down up front. And a lot of solutions coming out for that. It's really exciting to see. So now that we've seen the exteriors of buildings, I'd like to present Nick Brancaccio from Floored, and he's going to show us really high-quality interior renderings on the web using WebGL.
All right, hi guys. Thanks for having me. I'm Nick Brancaccio. I do lead graphics at Floored. Floored does real-time rendering of architecture in WebGL, in particular architectural interiors, which is what I'm going to be showing right now. So here's a live demo of our latest graphics chunk of work that we've been doing. What you're seeing here is a bunch of improvements. One is we have indirect diffuse and specular responses being represented. We have physically based exposure and white balance, as well as a physically based sun and sky model and physically based light temperatures. So getting all of these in together was very important to getting this final look. GI just on its own, but without a realistic dynamic range for a scene, doesn't get you a lot. You actually need all these different pieces. And so I just wanted to kind of go through a couple of the different layers that are happening to create this shot. So this first layer is just a kind of clay rendering of the scene. I don't have albedo multiplied on top of any of the materials, and metallic materials are not colored by their Fresnel response. So this just gives you a sense of the sort of general lighting in the scene. And maybe to toggle through these, I will stick on one space for a second. Okay, so yeah, here's our clay rendering. This is direct light only. So you can see without any sort of indirect response or skylight coming in, the scene is super dark. We can't just light a scene architecturally like this. This is diffuse only for direct. And then here we have the specular response for direct light. So you can see the specular mostly coming in from the sunlight. This is our new indirect light, which I'll talk about in a sec after I kind of show the different layers. Here is indirect diffuse only, and here's indirect specular. And so just to kind of go back and show you, one thing that we learned from this process was interior scenes really are affected a lot by indirect specular response. And so just doing a typical sort of spherical harmonic representation of diffuse only wasn't going to work for us. We needed this, you lose a lot of energy, between those two. So yeah, here's indirect specular. The way we're doing this is we're storing a 3D volume of radiance data. Right now we're emulating the volume, but I'm very much looking forward to WebGL 2, where we'll be able to actually have 3D textures and won't have to manually do this in the shaders. But yeah, so we're storing radiance in each voxel around this space. The representation is we're doing 8 spherical Gaussian lobes. So if you can imagine sort of a lobe going to one of each corner of a cube, and with width enough to cover the overall, to approximate radiance coming in over the sphere. This actually allows us to analytically integrate the incoming radiance and both the diffuse and the specular BRDF. So this allows us to get a indirect specular response, which you can see sort of this variation as I kind of go towards the floor, and this view-dependent response. So yeah. Go back to that view. Okay, so this is the diffuse and indirect now added together. And now we have emissive surfaces on top, so not a huge difference, but you see those lights at the top, and the TV is now on. And there's also this new histogram in the middle. So the way that we're doing automatic exposure is we are building a histogram of the scene, and we're using this histogram to be able to trim the distribution and get a trimmed mean. So this allows us to say, if we just take the mean of the scene, first of all, little specular hits that are highly intense are going to push off our mean a lot. So we want to trim those off. And we also want to allow a reasonable portion of the scene to be underexposed so that we have a contrasty scene with sort of local shadows going on, stuff like that. I believe my settings currently are about 25% trimming on the low end and maybe about 5% on the high end. Further, we can actually do some kind of interesting stuff here. Right now, this is one histogram for the overall scene, but I've started to play with doing multi-zone exposure. So now it's not super obvious because of how busy this scene is, but yeah, you can see a little bit better now. Now there are 4 histograms. So it's building a histogram for all 4 quadrants of the scene and then computing a good exposure value separately for each of those. And then sort of during the tone mapping phase, we're blending between them and getting a smooth exposure. You can start to really push this. You know, here's 4x4 exposure zones. And you can start to get really crazy and get some kind of nasty ringing effects and you can really start to flatten out the scene. So you don't want to go too far with it. We're still playing with this, but one kind of interesting thing for me with this was realizing that like our clients will often talk about wanting light, airy scenes. We've joked around in the office that they're afraid of the dark, and so we really needed a way to get well-exposed shots, but we also wanted these high dynamic range scenes to get physically plausible results. So for example, in this area, we have, if it's just one global exposure, that back area becomes quite dark. It's realistically dark, but that's probably too dark for what one of our clients would want. But now if we do this quadrant-based exposure, we can start to brighten that up. We're also doing dynamic white balance along with this exposure because we have these different color temperatures that we need to balance between. So that's basically it. I just wanted to end this live demo with sort of destroying the image a little bit. So we do temporal AA, and we can render the scene at different resolutions, which allows us to sort of target different hardware if we wanted to. So I can drop down now. Now I'm rendering it at a low resolution, but if I stop moving, it'll actually resolve to a higher resolution, which is pretty cool. But I can really push this too far and kind of get some crazy results. But you know, if I wait long enough, maybe it'll come in. Anyway, here's even lower. Thanks so much, guys.
Really great stuff, Nick. Looking really good. Okay, so now we're going to switch tracks a little bit and focus on GLTF for the remainder of the BOF. And I'd like to introduce Tony Parisi, who is the GLTF specification co-editor.
Hi, everybody. So I'm Tony, the spec co-editor of GLTF, a new file format for delivering 3D into web, mobile, VR, desktop applications. Other shout-outs to other people on the team. Patrick Cozy, stand up and wave. He's my spec co-editor. He's put countless hours into this. Thank you, Patrick. Remy Arnaud was in the original design team, formerly of Collada, helped us get this kicked off. Fabrice Robinet, who's not here, Uli Klump, other members of the team. Many thanks to them. It's been about 4 years now. So for those folks who don't know what GLTF is, I'm going to do a quick backgrounder. So the situation was this a few years back. We had a proliferation of 3D applications, mobile and web, with GLES and WebGL. And in particular with WebGL, we were feeling this pain, which was we didn't have any standard way to deliver data into the applications, at least not one that was efficient, could actually preserve full scene data, and wasn't tied to some specific engine or software vendor. And we did have standards out there. We had the OBJ file format. We all know that one. It's a great text format, but it just does meshes and materials, doesn't do cameras, lights, all this other fun stuff. We have Collada, which preserves all the information, but was never designed for web and mobile deployment. It's really big and bulky. It's an XML. It takes a long time to parse. Was really, something you use upstream from your application. And then there's a bunch of engines out there and tools out there that have their own file formats. Autodesk FBX is obviously really popular for modeling, but also not designed for web and not appropriate because it's vendor specific. And so we're feeling this pain a lot in WebGL, especially where people were bringing new applications online. As we know, WebGL doesn't have a file format, right? It's just a rendering API. And then libraries are built on top of that will parse data files and render them appropriately. And so people were creating their own pipelines over and over again. They maybe would get a Maya export that would go to OBJ, and then they'd have to call their guy down the hall, who was the technical person, and tell him to recreate the transform hierarchy or relight the scene. It was just absurd. And there were huge inefficiencies in that pipeline, so we decided to address that by creating a file format that everyone could work toward and basically share resources and all win. Beyond that, it was also really hard to then take that data and share it among applications unless they were all written with the same engine, right? So that's what GLTF is all about. You can kind of think of it, and this is a fairly precise analogy actually, as a JPEG of 3D. It's basically the file that's got all the 3D data in it. It doesn't have any behaviors, any runtime semantics at all. I mean, there's animation data in there, so that's a runtime semantic, but essentially, other than that, I mean, there's nothing that says when you click on this, this happens. Nothing behavioral or scripty in it. It's purely the 3D data. It's designed to load really fast over slow connections. It's not tied to a runtime, and it's designed to be extensible. We're going to talk about each of these things. And just a quick timeline. I don't love history slides, but it's just important to give you context. We've been working on this for about 4 years now. It started out with some very simple development where we thought we were just going to do static meshes, and then we realized before long, well, OBJ does that, why bother? And the use cases we were considering really needed full scene data and full animations and skins and all that stuff. So we spent a couple years developing, and then last year got really, really aggressive about standardization. This whole thing has been done in the clear, by the way, even though you need to be a Khronos member to vote on the spec. Anybody can participate and give feedback on the spec. Everything is done in the GitHub repo. All the issues that against the spec are done in the GitHub repo, all the spec design, all the discussions. We have an internal working group mailing list just for working group members, but everything else is open to the public, and so we've done it all in the sunlight. And last December, Khronos ratified this as a standard, which is great. That's version 1. And we are currently working on a 101 release this year, which is essentially just tightening up the spec language. I'll flash up the page really quick. This is the boring stuff. But this is literally the GitHub page and the GitHub issues for the kind of things we're going to tighten up in spec language. That's all it is, really. And so then, you know, conforming implementations would have to honor these rules. So there were some rules that were a little fast and loose. And we have not ratified this yet. This is all being, is being reviewed, but we will, go through a process of trying to ratify that soon. We're also kicking off a syntax validator. I'm going to talk about that in a moment. And at the end of the talk, I'm going to do a call to action for a roadmap for the next set of features, whether that's a 1.5 or 2.0. We don't have a version number on it. So here's what GLTF looks like. It's basically a JSON file. So if anyone knows JavaScript and JSON, it's a JSON file that describes the structure of the scene. And then all the other big data that would be bad to do in JSON, would be too bulky to do in text, is done in binary files. And those binary files are referenced externally from the JSON. So it's not just a mesh format. The binary file will have all the mesh data, but also have animations, also have skin data, inverse bind matrices, the kind of stuff you do in skinning. Shaders are in external files written in GLSL. All your texture maps are your standard web formats referenced externally. And then finally, you put these things all together, and any runtime that can read this stuff will put together, like Cesium, which is built natively, and it can render this stuff as a scene. There's an extension mechanism, which you basically just add extensions used to the top of your JSON file, and you can write any extension you want. Khronos has some standard extensions, and you can write vendor-specific ones too. This is a way to keep the spec really lean and tight, the core spec, but allow for experimentation. This is classic Khronos. This is the way OpenGL is done. This is the way WebGL is done. And a lot of people are adopting it. This is really great. So last week, Oculus got involved in this publicly. John Carmack gave us a quote. There's a few VR companies getting involved in this now. Otoy. We're going to see a presentation from Oculus soon. And there's all kinds of tools and vendors getting on board with this. I'll give you a quick snapshot of the ecosystem in a second. But here's the deal. With new formats, we have new opportunities. This is not just about greasing the skids on the graphics pipeline and the production pipeline. But once you have a universal format for your 3D, you now can share it among applications the way we can file share JPEGs or videos on YouTube or what have you. So think of the possibilities there. I'm tight on time, so I can't really go through these in too much detail. So I'm going to blaze through all these. But these are many of the pieces of the ecosystem coming out. Converters from Collada, the spec validator. We have a MIME type that's official now. Woohoo! Thank you, Uli Klump, for driving that through. Autodesk has written a converter from FBX. Oculus is going to show you one really soon here. And we have a whole list of tools and an ecosystem up online. These slides will be shared. Give me 20 more seconds, Ken. Hit the stop button. There we go. Yeah, so there's this open source validator project with which Alexei Kniazev, how do you pronounce that, Patrick? Alexei, I haven't met him yet, we've been working remotely, has written something in the Dart language, which is a client-side validator that you can drop in and basically run over your GLTF code. This is going to help grease the skids on conformance so that, basically you will know if you have a valid GLTF file before you try and put it in production. So this is a Khronos project, and we're rolling it out, and it's going to be tied to the 1.01 specification. And really quickly here, because I'm essentially out of time, we're kicking off a new roadmap. If anyone wants to come talk to myself or Patrick or Neil Trevitt, who's basically been acting as the chair, Neil, you're here somewhere, wave. We all know Neil. Come talk to him and get involved in GLTF. And there's a lot of different areas we want to get into. We want to get into WebGL 2, adding new data types that might support anything we might be missing, because this was all based on WebGL 1. Physically based rendering, we're contemplating extensions now and having discussions with Fraunhofer, the team from NVIDIA on MDL. Morph targets, spatial partitioning, bunch of fun features that we'll do as extensions first, and ultimately some might be part of GLTF 2. So with that, all I want to say in addition to that before we see these great GLTF presentations is There are t-shirts outside, like this one. Go get one. Thank you.
It's incredible to see the momentum behind GLTF, and Tony and Patrick have just done a fantastic job in driving it and getting all of this adoption across the industry. And a very exciting partner in GLTF is Oculus, and we are honored to have Amanda Watson here to talk about what Oculus is doing with GLTF. So welcome.
Thank you. Okay, cool. So I'm here specifically to talk about virtual reality on the mobile platform. And if you're not particularly familiar with the specific characteristics of VR on mobile, that's actually sort of fine, because pretty much every good or bad thing you're going to hear about development right now is just going to come down to the fact that it's new, right? All of it. You've got a new platform, a new medium, and a new ecosystem. And with so many unknowns for established content teams to tackle, one of the best things that we can do with a choice of a format or a standard is to ground mobile VR development in something that's known. So when we choose standard formats for mobile VR, we're always going to try to consider what's going to open up development to the widest range of engineers and artists. You know, can we choose a standard that integrates well with a major modeling package? Can we choose a tool that's widely accessible to anyone who wants it for free? Are we helping our developers remain a part of that greater community? So when Oculus was choosing a scene format a couple of years back, we were asking ourselves these questions, and we arrived at a place I suspect a lot of companies do end up at, that the least of all our evils was going to be a new internally developed format, and we call that OVR scene. Okay, so, you know, there's a valid question, which is OVR scene helping us be inclusive? Well, yeah, I mean, sure, it's not a part of an existing tool chain, but one of the biggest struggles our developers face is rendering performance. And the thing that OVR Scene did is broke things down in a way that made high-performance rendering easy. But we still miss out on a lot, because unlike GLTF, OVR Scene isn't externally supported. It isn't open. And if I have time, okay, I have a little bit of time. I do want to make it really clear that the GLTF kind of open is the open that we mean. I think people get really cynical about community-driven universal standards as solutions, because folks always point to the long history of community-driven efforts that fail to solve problems, you know, compared to proprietary equivalents, right? But, you know, the thing is, platform creators have to look at history a little differently, and what you see really, really clearly with the rise and fall of platforms over the last 30 years is what only community-driven efforts have been able to do. And it should really strike fear in someone's heart that no single entity has ever found a substitute for an active community-driven ecosystem. And with that in mind, we know that even if our internal format is inclusive, even if our internal format has the same level of third-party tooling, which it doesn't, we should still have a problem because it isn't fundamentally open. So why are we choosing GLTF? Well, as you can see when you compare them, they look really, really similar in the scene breakdown. And when we looked closer, we realized that more or less we could get all of the optimizations that were necessary for high-performance rendering without constraining the GLTF spec. In addition, we get tools, we get community support we wouldn't have had, and it was an easy decision. We basically hit the ground running. So Oculus is involved in the continued development of GLTF for the entire community. We've implemented support in our own SDK, and we've concocted this thing we call FBX to GLTF. It's a command line conversion tool. It's derived from the original FBX to OVR scene converter we were handing out to developers. And it brings along many of the performance optimizations that were making scene rendering performant for mobile VR. Right now, this converter sort of has limited support for some of the features. It had a ton of variation between formats, things like animations. But the good news is we're actively working on making this project available to the community open source. So I'd like to go over some of the things FBX to GLTF is doing to make scenes VR ready. Well, so first of all, one thing we know from mobile developers bringing their content to the platform for the first time is they're often penalized by the disproportionately high cost of individual draw calls on the mobile platform. The converter mitigates this a bit by finding opportunities to combine FBX meshes into a single GLTF mesh the renderer can draw as a single surface. The converter also includes this cool tool that will return the texture LOD from a fixed or limited range of vantage points, and developers can use this to then go back to their tools and re-optimize texture usage. There are also several options for optimally sorting geometry, so you can minimize the number of shading operations, and that includes sorting along an axis for a fixed vantage point. And as we continue to work with Khronos and the 3D formats group on GLTF, we also plan to add in more GLTF features, as well as some of the more complex features we weren't able to bring around from our old pipeline, such as optimized data structures for collision detection and gaze selection, and that support for more complex animations. And so now I have a demo. It's going to be the most interesting scene loading demo you've ever seen. This is me loading scenes with 2 different formats at the same time. And what does this prove? This proves that we have something up and running, and it proves that from a rendering perspective, nothing really changes with GLTF. We still get the same high-performance runtimes and high-performance rendering we've always had. But I think for developers, GLTF is really going to change everything. They're going to be able to integrate with major modeling packages. They're going to be able to have access to robust tooling. And really importantly, they're going to actively benefit from the cooperative efforts of an incredible community. I'm really excited about the future, and I think we look forward to working with all of you. Thank you.
Thanks, Amanda. That was awesome. And it is just really exciting to see Oculus using GLTF. All right. Okay, so for our final presentation, I would like to welcome Fraunhofer to the stage, and I think we have Timo and Max here?
Exactly.
Okay, fantastic. And they're going to show you physically based materials in GLTF. All right, this is where it's at.
Okay, thanks a lot. So, a lot of exciting stuff going on related to GLTF, and what we are going to show you as soon as the presentation is on there is, PBR and GLTF. And you have seen that gun before. Can we get it also in 3D somehow? Oh, yeah, okay. So physically based rendering, I guess it's nothing new for most of you, but it would be exciting to have a format where we can easily specify assets like that in GLTF without having custom shader, technique, etc. code. And that's actually what we want to do. And as we're always showing cars on the WebGL BOF, to keep consistent with that, here's another German car. But this time, I think it looks a lot nicer. And having such a WebGL application is really useful in several scenarios. So for example, product configuration, or design studies. So we can play around with different finishes, different lighting situations, and then you can visually evaluate the quality of the surface, for example, which is very important. So yeah, let's go to the presentation. Thanks, Timo. So as I said, we're not having an easy way of defining physically based rendering materials in GLTF at the moment. We are having materials common, which is a great extension to specify simple Blinn-Phong materials in just a very few lines of GLTF. And we want to have something similar for PBR-ready materials. So we did a small case study and looking at different engines and how they specify their assets for PBR and which kind of models they use. And surprise, the outcome is there is no single common parameter set that you could just take out of the box. But the good news is, on the other hand, that there are the same frequently used common terms and material properties, and you just have to sort them kind of and get an overview, and then you can easily create some parameter set that can probably be used among all kinds of engines with minimal adoptions in their pipeline, and they can easily load and render it. So the used shading models are very similar. And so we heard it already today. At some point, there's usually a specular BRDF and a diffuse BRDF. And for specular, you have this Cook-Torrance microfacet model, which is, I guess, the very most popular model, and it has these different terms like normal distribution function, Fresnel, geometric self-shadowing, and for all of those you have different approximations. But that's nothing we want to specify. So we don't want to have people being forced to use a specific approximation. Instead, we're just saying, okay, if you have this asset and you want to render it, for example, on a mobile device, you are free to use another approximation than if you render it on desktop. But what we specify is a common parameter set, and that's what we came up with. So you remember, for example, yesterday in the real-time live session, there was this mobile demo with the state-of-the-art rendering, and then they did a split screen in between, and they had a metallic and smoothness map. So what we have here is metallic and roughness as one model, and so it's easy to convert one into the other inside your pipeline when you're loading the asset and for rendering. And the other model is the diffuse specular glossiness model, and you can find all the details on GitHub. So I don't think I need to go into details here, and it's open for discussion. So here just a very brief example how it looks like. If you want to shade this happy Buddha with this rough or brushed, I don't know, golden material. So you specify a base color, metallic factor, and roughness factor. So in this case, we picked the metal roughness technique, and this comes with our materials PBR extension. So it's currently having a vendor prefix since it's just a proposal, and it's open for discussion. So check it out, go to GitHub, check out the pull request. There's already some discussion ongoing and already some proposals. And we're quite excited to see this as soon as possible in GLTF as an extension. So thanks a lot.